Hey, welcome back. Today we're going to be talking about projectile motion. We've just finished up talking about gravity, and this is kind of a natural follow-on to the whole gravity thing, where we're going to be integrating what we've learned in terms of linear motion with what we learned from the gravity lesson. So there's some really cool stuff that's going to come out of this, and at first it's going to seem pretty straightforward, simple, and then it's going to get a little more sophisticated, and by the end we're going to be doing some amazing calculations and inferences about the nature of the universe and space-time itself. Projectile motion is what makes all of this possible. So we're going to come right up to Einstein, and then we're going to stop right there. We're going to leave Einstein for the fun part right at the very end. We'll come back to him later on. But you'll get an idea of where this is going by the end of this lecture. All right, so with projectile motion, there's some fascinating things that we need to keep in mind. First off, without gravity, a tossed object follows a straight line path. Right? This is something that has been observed since the days of Aristotle. So you take an object and you throw it or you move it or whatever, and it's just going to keep going in a straight line. And I'm sorry, I said Aristotle, since the times of Galileo. It's going to go on a straight line path. Okay, so with gravity, the same object tossed at an angle follows a curved path, right? So without gravity, it goes in a straight line, but with gravity, gravity is pulling on it and exerting a force, and that force causes it to change or accelerate into a different direction. Remember, acceleration is a change in path as well as a change in speed. So a projectile is any object that moves through the air or space under the influence of gravity, continuing in motion by its own inertia. All right, so projectile motion is a combination of two different movements, right? Two that we're very familiar with, right? We're familiar with linear movement, so here's a ball being rolled across a table in this direction, and which is to say it has an x direction component, and it also has a y direction component, which is an acceleration. See, notice this is not accelerating, this is constant velocity, but this is constant acceleration in this direction, all right? And this is important to know, right? If you're going to fire a cannon, turns out the cannonball, as long as there's no air resistance, of course there is air resistance, but this gentleman is firing this cannon. The cannonball is going to come out at some velocity x, and it's going to be following this line of physics right here, right? Constant velocity all the way out of the cannon and into its target. So the target's going to be hit at about the same velocity in the x direction. But the y component, as soon as the cannonball comes out the muzzle of the cannon, it begins to drop. The cannon actually starts to, or the cannonball starts to fall. And so as a consequence, they have to point it up towards the air so that it doesn't hit the ground before it hits its target. All right, so we know that. Let's go over the physics of it, right? So make sure you understand there's two components, an x direction and a y direction. So let's look at the case of projectile motion where you got projectiles launched horizontally. So here would be a projectile on a table. We're going to say that there's no gravity. And if you were to launch it off this table, no gravity, it would just continue straight across with constant velocity straight across in this direction. All right, here's vertical motion only with gravity. So here we've got it on the edge of the table. We drop the ball and it accelerates, right? So each successive second or moment of time, it increases by that amount. So remember, that's the nature of an acceleration. So when you combine them, it turns out you can take this time and 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 compare it to these times, and you get this nice curved path. So this is the combined horizontal and vertical motion. And you can actually superimpose both these graphs on one another, and here you can see that you see both components arriving or occurring at exactly the same time. So here it is falling down like this, and as the moment it's here, and over here, this curved path would be right here. So we could actually see the ball would continue down with these two components. All right. So it turns out that gravity is not being interfered with by the fact that it is moving in a vertical, or I'm sorry, a horizontal velocity. The force of gravity still pulls down normally. All right. So let's see what we have here. The horizontal component of velocity doesn't change when air drag is negligible. The ball travels the same horizontal distance in equal times. Okay, we've gone through all that. The curvature of path is the combination of horizontal and vertical components of motion. So that's what we're seeing right here in graphical form. Cool. So The projectile motion, it turns out, takes a curved path, and that curved path is usually described as parabolic. So this is a parabola right down here, moving up along this path here, and then back down. And of course, if there's no ground here, it'll continue down in the direction of this arrow right here. So a curved path of a projectile that undergoes acceleration only in the vertical direction while moving horizontally at constant speed. All right. Paths of projectile following a parabolic trajectory. These are what we're going to see. The horizontal component along the trajectory remains unchanged. In other words, you see this arrow here, this is the horizontal component. Notice it's the same length in each one of these. So that never changes. But the velocity at any point is computed with the Pythagorean theorem, diagonal of the rectangle. So here we have a component of acceleration up that is exerted by the force of the cannon or whatever it is that's firing it up into the air. Of course, this is constant in each one of these cases. It's just v. And if we want to know the direction or the velocity at any point, it's just a squared plus b squared equals c squared, Pythagorean theorem. We've done this a little bit earlier in the class, but you can see that there's a triangle that's formed right here. And that hypotenuse is what we care about. That's going to give us the velocity at any given time. Now notice as it hits the ground here, that hypotenuse or that angle, or I'm sorry, that arrow right here is the same length as this one over here. And we would expect that to be so because of conservation of energy, right? When it goes up, it's going to come down with the same velocity that it went up. Okay, cool. All right, let's look at the way that a cannonball shot at an upward angle would behave in the field of gravity, right? We tend to fire a cannonball, and we like to think that it would just project up forever in this direction and eventually go out into space. But what's happening over time is that gravity is actually exerting some force on the cannonball. As soon as you fire the gun, actually, the cannonball starts to fall off of this trajectory. And you can figure out exactly how far it's going to fall off of that trajectory using a relationship we were using earlier in class, right? 5 times t squared. This was something that you had seen when we were talking about linear motion earlier in the class for things falling specifically. So 5, or sometimes you would see it as 4.9 t squared. Let's see here, 1 second. We would see, does this make sense? 1 second squared is 1 times 5. Yeah, it's dropped 5 meters. What about after 2 seconds? Well, 2 seconds squared is 4 times 5. That's 20 meters. Yep. So this is what's happening here. So it's basically, you can take this nice little equation right here, project up a nice path, and then you could subtract off the gravity at each time, and you can draw a nice smooth curve through here, and you can see that that's what they've done. So after 3 seconds on this trajectory here, it looks like the cannonball is just about ready to hit the ground again, right? It actually has not gone very far. Projectiles launch at an angle. The laws of physics aren't going to change just because we throw it up or throw it down. So here we see some stones. There's a student who's throwing stones off this cliff. Perhaps there's an ocean down here or something. In this case, they're throwing it at an upward angle, and here they're throwing it at a downward angle. It's not going to change anything, right? The fact that you've thrown it up at an angle, it's still going to lose after time 1, time 2, time 3, time 4, the exact same amount. Here's time 1, same amount. Time 2, same amount. Time 3, time 3, you get the idea, okay? So those things aren't going to change. Gravity is still going to accelerate at exactly the same rate, okay? What about as it goes out in this direction? Hey, check this out. It turns out that the velocity is still going in this direction, all right? So as long as you know where you're projecting that stone, you can go ahead and subtract off gravity and be able to plot out that nice curve if you wish to do so. This is really useful, by the way, if you're involved in warfare. Some of the best mathematicians were employed by the military, even to this very day, to deal with these types of problems. Okay, so projectile motion has some really cool features that we should know about. First off, you can get different horizontal distances resulting from just changes in the angle at which you are lobbing the object. Okay, So same range is obtained from two different launching angles when the angles add up to 90 degrees. What does that mean? Well, it turns out that if the angles equal 90 degrees, so 75 degrees added to 15 degrees is going to be 90 degrees. So what does that mean? Well, 75 degrees goes way up high and then it drops back down. But look, if you were to just launch it at 15, it does exactly the same thing. It's much less spectacular, but nonetheless, there it is. So by that argument, we would expect 30 and 60 to be the same. Sure enough, here's 30. Lands right here. 60 goes way up and lands right over here. And of course, to get the longest distance, it turns out, is to hit it at a perfect 45, or to launch it at a perfect 45-degree angle. And it will wind up over here somewhere. Okay? Pretty cool stuff. So as long as you know that if they sum to 90, for example, if I asked what would be the other angle that lands at the same position as a 20-degree shot, you would know that 20 degrees subtracted from 90 equals 70. So 20 and a 70 degrees would both land at exactly the same place. All right. So, but the problem is that we're dealing with a situation in that former scenario where there's no air resistance. Of course, on planet Earth, there is lots of air resistance, and we need to keep that in mind. So while the maximum range occurs for an ideal launch at 45 degrees, with air resistance, the maximum range occurs for a baseball batted at less than 45 degrees above the horizontal. And the reason why that occurs is because the air resistance tends to knock the ball down. It keeps it from wanting to explode up and get its full height. So one of the things that is easier to do is to hit it at a lower angle and let velocity really take over. So it turns out that the best angle to hit a baseball at on planet Earth, now if you're on the moon you'd want to hit it at 45, but on Earth it'd be between 25 and 34 degrees of an angle. With air resistance, the maximum range occurs when a golf ball is hit at an angle of less than 38 degrees. So you'll notice that whenever you use a driver, which is a type of club used in golf, it has a pretty flat face on it. And essentially what happens is it hits the ball, and then the ball gets enough backspin where it actually spirals up into the sky at about a 45-degree angle. But you don't actually hit it at that angle. Okay? And here's this is Vladimir Guerrero, a recently retired baseball player, hitting a home run, and look at the angle coming off there. That's at about 30 degrees or so, maybe 29, 30 degrees. And this is actually one of his famous home run hits. He'd hit these things forever. These things would just basically explode off his bat. All right, so let's talk a little bit about kind of what happens when something is launched pretty much straight up in the air. Well, without air resistance, the time for a projectile to reach maximum height is the same as the time for it to return to its initial level. So in other words, the amount of time, the hang time, the amount of time it takes for it to go up is equal to the amount of time it takes for it to go down when there's no air resistance. And of course, why would we expect this to be so? Conservation of energy, right? You put in a bunch of kinetic energy here, it turns into potential energy, and that potential energy is discharged back. And remember, potential energy turns into kinetic energy, which is dependent upon velocity. All right, neat. So let's actually step up. Let's go away from baseballs and golf balls, even though we tend to think of those as fast-moving projectiles, even bullets. We need to talk about things that are even faster. Satellites. Satellites go much faster than bullets. So satellite motion is an example of a high-speed projectile. Satellites go at extremely high velocities. A satellite is simply a projectile that falls around Earth rather than into it. So basically, imagine you have a ball, and here's Wonder Woman wearing a pink shirt here, and she throws her her satellite off this globe here. She's, keep in mind, this is all fictional, right? No really large women in real life. But anyway, she throws the projectile, and she throws it so hard that it starts to move away from the planet, but the planet, of course, is always pulling it towards her. And so here's the path, it's pulling it towards her, but it never actually gets to the point where it lands, and it just continues to come back around, and it hits her in the back of the head. In fact, this was the exact scenario. It wasn't actually with a woman, it was with a cannon. But when Sir Isaac Newton put together his laws of gravitation showing that that gravity fields that affect things on Earth could be used to explain things in space, he used a cannon that would fire this thing, and the cannon would just continue, the ball would just actually go into orbit around the object, using the same argument. All right, so with no resistance to reduce speed, a satellite goes around Earth indefinitely. There's no reason why it would fall out. As long as it's going fast enough that it can get in front of its falling. Remember, it's always falling back towards the Earth, as we'll see in probably the next photo. As long as it continues to do so, it will never actually come back to Earth. It will just continuously circle around. So the reason why this occurs is because of the curvature of Earth. So Earth's surface drops a vertical distance of 5 meters for every 8,000 meters tangent to the surface. So tangent just means this. You take a straight line that just touches the surface of the curvature of the Earth and project it out. Well, look at that. So for every 8,000 meters, it drops 5 meters. So every 8 kilometers, it drops 5 meters. That's not an insignificant amount of curvature. That's actually a considerable curvature for the Earth on average. And this is a wonderful number, every 8,000 meters, because remember, our fall is to be for every second, it drops 5 meters. So that means we've got to cover this amount of distance, 8,000 meters, before we fall, because the Earth is going to be pulling us down at that rate. Every second is going to pull us down 5 meters, and we want the Earth's curvature to fall away or to drop away at the same rate that we're falling towards the Earth. And that way we never run into it. That's how you get an orbit. Okay, so how do we position our satellites then? Well, first off, we need to keep in mind that there's several ways that we could position them. We could put them into circular orbits, and there's another kind of orbit called an elliptical orbit. We'll talk about the circular ones first. So the positioning is usually beyond Earth's atmosphere. Or in a matter of fact, in all cases, beyond Earth's atmosphere, because air resistance is totally absent in space, or almost totally absent. So an example would be a space shuttle, which would be launched to an altitude of about 150 kilometers or more to be above air drag. It does turn out that it does experience a little bit of air drag, not much, but even as we note here, that the International Space Station, which is currently in orbit, it does experience some air drag, and every once in a while they get a boost, they hit the booster rockets, and they push themselves back up into a higher level, or a higher orbit. But over time, the drag starts to pick up on it. It reduces or it increases the degree of falling to the point where the space station starts to move towards the Earth. So they overcome it by boosting back up a little bit higher. Cool. This is, of course, is the space shuttle back here with the moon and the Earth. So here you can see the curvature of the Earth beautifully. Right? You just want to make sure that if you're going around the Earth, you're going fast enough that the Earth is curving away at the same speed that you're falling towards it. Otherwise, you're going to hit it. We'll come to this picture here in a minute. This is a really neat photograph, or a neat artistic image, actually. So circular motion moves in a direction perpendicular to the force of gravity acting upon it. So at no point are you actually going to be in the same direction as the field line. Remember, we're talking about the gravitational field lines. You're going to be perpendicular to it, or what we'd say orthogonal to it. So you're going to want to be going, if this is a field line, my finger, you're going to be going in this direction, right? It's going to constantly be pushing you down, but fortunately you're going to be falling, let's see if I can show it better. You're going to be falling at the same rate that the Earth curves, all right? So you're going to be continuously hitting these field lines, but these field lines are really going to be inconsequential to you because you're never actually going to hit the Earth. All right, so for satellites close to Earth, things that are just barely outside of the atmosphere, it takes about 90 minutes for them to orbit the Earth. They're going quite rapidly. So about every 90 minutes, they orbit, okay? But for satellites at higher altitudes, especially like GPS satellites, things that are way far out, longer periods, up to 24 hours are common. Geostationary satellites are kind of the most common version of the longer period ones. All right, so what are these things over here on this image? This is a map of all of this orbiting space junk and satellites and garbage that's now been put into orbit by human beings around the Earth. So the Earth is actually represented by this ball here, and actually all the white stuff that we see here is all the stuff in very low orbit around the Earth. This material out here, especially this outer ring, this is usually your communication satellites, your GPS satellites, you might have some spy satellites, other things like that. That's what we see out here. We see a bunch of other material that's going around, say old fuel tanks, broken parts of spaceships during launches, you name it, it's all up there. And so there's about 370,000 little pieces of space junk up in space. And it's becoming a problem because these things are going at very high velocities. And you basically have created a gallery of space junk all around the Earth. And at some point, this has got to be dealt with, right? Because these things are going at such high velocity. If you hit one of these, it just rip your spaceship in half. Okay, so the other kind of orbit are the elliptical orbits. So a projectile just above the atmosphere will follow an elliptical path if given a horizontal speed greater than 8 kilometers per second. Remember, 8 kilometers per second is the same thing as 8,000 meters per second. That's what we're talking about, the curvature of the Earth before. So if you get faster than that, it turns out you're going to create an elliptical orbit. So an elliptical orbit is basically what we see here. We're going to get into some detail about this. But it's a special kind of curve. It's an oval-shaped path. And for example, a circle is a special case of an ellipse when its two foci coincide. So foci are these points here. Now notice that this person has taken a pen and is making an ellipse in this way here. These foci are the places where you would attach a piece of yarn or string, and then you could go ahead and draw all the way around here and you would get the path of an ellipse. Right? This is a little different than a parabola. It's actually a lot different than a parabola. But nonetheless, you understand there's a curved path here that loops in on itself. All right? So a circle is just a case where this tack and that tack are together right here in the middle, and they're spiraling around. So an ellipse is a special case where they're not stacked on top of each other. Right? I hope that makes sense. Okay, so let's talk about the nuts and bolts of elliptical orbits, specifically the speed. What's interesting about a circular orbit is that the speed is constant. It never changes. But in an elliptical orbit, it is constantly changing. The satellite will be accelerating, slowing down, decelerating, so on and so forth, changing paths. So initially, if the speed is greater than that needed for a circular orbit, in the case of Earth, it would be over 8,000 meters per second, satellite overshoots a circular path and moves away from Earth. Okay, so this is what we see here. Here's the launch, comes off like so. The satellite loses speed and then regains it as it falls back towards Earth. So here it's coming up, it's moving, it's gone too far. It didn't go into a nice circular path. It actually goes way up and it starts to slow down and it begins to fall back towards Earth. And it basically rejoins its original path with the same speed it had initially. So here we see it looping up, slowing down, and then speeding back up, and then going around in the circle. And the procedure is repeated over and over and over. And this would be an elliptical orbit. And this is what we see here. Here we see a object that's orbiting another object. Let's say that this is a satellite that's orbiting the Earth, and it's in an ellipse, right? So here is a focus. There's another focus over here, but it doesn't really matter. It turns out the planet has just got to be one of the foci. All right, and so you'll notice that when it's out over here, it's moving slower, picks up speed, and its fastest point is right next to the planet as it goes by. Look at this. Cool. So the guy that put this together was a guy named Kepler. So Kepler, who was Kepler? Kepler was assistant to the famous astronomer Tycho Brahe, who directed the world's first observatory. And Tycho Brahe, there's all kinds of interesting stories about this guy. Some people say he had a gold nose, the whole thing, right? Fascinating individual. But Kepler did some interesting stuff too. One thing that Brahe was good at was getting very good data. So Kepler basically took some time and he used the data that Brahe had collected on planetary motion to figure out the motion of planets. And what he discovered was kind of revolutionary at the time. You know, a lot of people believe that the heavens were this celestial sphere put together by the gods and so on and so forth, whether it was the Christian God or the Muslim one or whatever. But the idea was that the celestial realm, the heavens, were perfect spheres everywhere. Everything orbited in perfect circles. But he found something different. He said he found that the motions of planets was not circular, rather it was elliptical. Okay, this isn't going to make you real popular in a world that has believed that Aristotle and his idea that things moved in perfect circles, and other people with their epicycles, another astronomical concept that we're not going to cover. This would make you a very unpopular person to make this observation, but nonetheless, it was correct. And Kepler happened to come along at a time in history where there at least were some people willing to listen to what he had to say, and we were able to build off of his ideas. And so he came up with some laws of planetary motion, and they basically hold to this day. We use a little more sophisticated way of looking at them now, but it was a good way of making sense of the heavens. Right? His first law was that the path of each planet around the sun is an ellipse with the sun at one focus. So this would be the sun, and there's an ellipse going around it. This would be the path here. We'll get to the ABCD here in a moment. Second law. Now this is a little more difficult. This is a geometrical argument, so be prepared for this. The line from the sun to any planet, so let's say here's the sun, and we're going to draw a line to planet at, say, position B. Sweeps out equal areas of space in equal time intervals. So in other words, if at time, the period of time goes from B to A, this area here, the shaded in area, if it happens to be the same amount of time as for it to go from C to D, these areas would be exactly the same. Okay? And we do, in fact, observe that to be so. His third law was the square of the orbital period of any planet is directly proportional to the cube of the average distance of the planet from the sun. And this is for all planets. So it turns out that if you know how long it takes a planet to go around the sun, and you know its radius, you can apply that to all the planets. So suddenly being able to figure out how far away Mars was and how far away Jupiter was, if you knew how long it took for those planets to go around, and you knew this relationship, you can actually figure out how far away from the sun these things were in general because of the proportionality of these things. Absolutely ahead of his time. I don't know that if I had this data, I could have made these same interpretations, right? But the man was an absolute genius. Okay, so we've been talking a lot about how objects are speeding up while they're in orbit, especially if they're in an ellipse, and they're slowing down, and the velocities are constantly changing. You might be asking yourself, well, how can that not be a violation of energy conservation? Remember, energy is constantly changing form. It can change from kinetic energy to potential energy. So recall the following, that an object in motion possesses kinetic energy due to its motion. An object above Earth's surface possesses potential energy by virtue of its position, right? So satellites in orbit possess both kinetic energy and potential energy. And so at all times, what's really happening is as it's speeding up, as it's going into that ellipse, orbiting around and speeding up near that one focus, what's happening is a lot of that potential energy is being converted into kinetic energy, and then as it goes away from that focus and starting to slow down, it's actually converting that kinetic energy back into potential energy. So it's just simply doing a conservation of energy. So the sum of the two, however, is constant at all points in the orbit. So just because it's not circular doesn't mean that conservation of energy has been in any way, shape, or form violated. In fact, let's look at the case where it's in a circular orbit. So the potential energy and the kinetic energy in a circular orbit look like this, right? The force of gravity is down, the satellite is moving around, and notice in all these places the force is equal because the distance is equal. So potential energy and kinetic energy are also equal, or constant, I should say, not equal. But this is equal to this, and this is equal to this one over here. So the distance between the satellite and the center of the attracting body does not change. PE is the same everywhere, and the same is true, of course, for kinetic energy. Let's look at the ellipse. So an elliptical orbit varies. The potential energy is greatest when the satellite is furthest away or farthest away, and that's called the apogee. So where are we going to see the apogee? Well, here's a planet, say this is Earth. Here's our elliptical orbit around it, and right here at this position furthest away, that's the apogee. That's where potential energy, notice how it's marked as a big PE right here, is the largest. And of course on the opposite end of this is going to be the perigee. And the perigee is where we're getting the largest kinetic energy. And so it's simply going slow and accelerating here. And once it gets to this point, kinetic energy plus potential energy is the same as it is over on this side. So there's some symmetry actually to this ellipse. And it's going to speed up into this kinetic energy and then begin to start converting it back into potential energy. They get equal again, and then back up here where potential energy dominates. But notice that what happens as we go around this is that every point in the orbit, the sum of the KE, which is the kinetic energy, and the potential energy is the same, right? So the sum never changes. Conservation of energy holds true even in elliptical satellite motion. All right, so before we can finish our conversation on projectile motion, I think that one of the most fascinating parts of this is this concept called escape speed. Escape speed suddenly opens up a whole new dimension to everything we've been talking about. So voyages to the moon, Mars, and beyond begin with launches that exceed escape speed from Earth. What is escape speed? Well, remember, just to go into orbit around Earth, you have to be going 8 kilometers per second, or which is, say, 8,000 meters per second. You're going very fast. But to actually leave Earth and to break the elliptical orbit, you've got to go a lot faster than that. You've got to go at about a little over 11 kilometers per second. All right. So it turns out that it's a nice little equation. We're not going to derive it. You're just going to take my word for it that it exists. It's come to us from heaven, and it's a wonderful equation. And it's this one right here. So we want to know the escape velocity for any planet or any object in the solar system, or any object anywhere. Its velocity equals the square root of 2m, where m is the mass of the planet or the object that you're trying to escape from, times the gravitational constant. We know what the gravitational constant is from our last video, divided by the radius, or the distance to the edge, or in this case, the radius is from the distance from the center of mass to the edge of the object. All right, and we can do some fascinating stuff with this, and this is kind of how we're going to finish our conversation with gravity and projectile motion, and even finish our discussion of Newton and all of his marvelous ideas, at least for now. Newton is never gone, right? He'll come back at a later time. But at this point, we're going to finish up our unit with these things. So let's talk about escape speed. Okay, so one of the coolest ways to study escape speed, we could look at the Earth, we could look at the Sun, but the coolest way to look at it is to look at these supermassive objects that happen to exist in space. So let's look at, say, for example, this supermassive object at the center of the Milky Way galaxy, and it's a big object called Sagittarius A. This supermassive object has a mass of 4.1 times 10 to the 6th solar masses. That's 4.1 million solar masses. That means suns. And a diameter of, or at least a measured diameter of 12 million kilometers. That's a really large star, to say the least. What is the escape velocity for Sagittarius A? Now, we got a little note here. One solar mass is 1.99 times 10 to the 30th kilograms. And we have this other cool relationship down here we've been playing with. Escape velocity is equal to 2 times the mass of the object. We know what the mass is. It's 4.1 million times the solar mass. The gravitational constant, g, we know. And r, which is the radius. So g is 6.77 times 10 to the negative 11. Now, when we're dealing with large numbers like this, again, the spreadsheet is by far the best way to go about doing this. And incidentally, this is an artist's conception of what Sagittarius A actually looks like. We'll get into kind of what all this stuff is that's going on in here, but it's really cool stuff. Okay, let's open up that spreadsheet. Okay, we're back. So here we've got our spreadsheet. Notice I've filled in some information. Sagittarius A's mass is 4.1 million solar masses. A solar mass is this amount here. So we're going to have to convert this into kilograms here in a moment. The gravitational constant we have, and we have the radius of Sagittarius A, which is 12 million kilometers. Okay, cool. So we have everything we need to calculate our escape velocity. So let's just start on it. First off, let's figure out what the mass of Sagittarius A is in kilograms. So we just do that by multiplying these two numbers here. So let's write that like this. Sag A asterisk mass. We'll put the kg like that so that we know, oops, we should do that lowercase kg, so we know what the difference is. Put our unit here, kg. All right, let's multiply that. So this times the solar mass. All right, so this is the mass of the supermassive object. 4.1 million suns all in one single object. That's a huge object. All right, so now it's very straightforward. We've got 2, that's just a constant 2, times the mass, which we just calculated, that's right here, times the gravitational constant, which we know is right here, and they're divided by the radius. Okay, so the radius is in this number of kilometers, so we're going to have to convert that into meters. So we'll do that here in a moment. So first off, let's write in our numerator. Our numerator is equal to 2 times Sagittarius A mass, which is that number, times the gravitational constant, which is this number. Okay, so we get this really cool number here. The denominator is going to be equal to 12 million kilometers, but of course we want it in meters, so we're going to multiply that by 1,000. Okay, so we know that that's going to be in meters. I should put that in meters there. And don't worry about the numerator units. We'll do the unit analysis another time. So now we have these two things, we can divide them. So let's put a note that we're going to divide them. Divided value. Fix that. All right, so we're going to divide numerator by the denominator. Look at this number here. All right, but that's still not going to give us our escape velocity. Our escape velocity is actually, if we were to do the unit analysis, would be in these things called meters squared per second squared. That's not really going to help us. We need to get it all the way down to meters squared. And of course, we notice that there is a radical sign above this whole thing. So we need to take the square root of this number, this divided value. So we're going to take the square root. So we'll call it the square root value. And so the way you do that is you usually just put in SQRT, and then you click that value and put it in your spreadsheet. And check this out. We get 3 times 10 to the 8th. This is in meters per second. Just take my word for it right now. That is a really interesting number. 3 times 10 to the 8th meters per second. Why? Because it turns out that the speed of light is also 3 times 10 to the 8th meters per second. Okay, these numbers are actually the same number. What does that tell us about what's going on at the surface of the supermassive object? It means that the surface of the escape velocity for the surface of the supermassive object is the speed of light. That is a fascinating conclusion to come to. That leads us to only one possible conclusion. That Sagittarius A has to be a supermassive black hole. Okay? That is absolutely interesting. The only way we could have figured that out is by actually doing the escape velocity. Cool. So let's go back and see what this all means. Okay, so we're back to our image here. And we see that there is a supermassive black hole right here. And notice that in this area here, we get nothing but a big dark spot. That big dark spot exists because we can't see into it. The escape velocity is greater than that for light. It's actually equal to the velocity of light. And as you go into that sphere, deeper into that region of space, it turns out that the escape velocity actually increases beyond the speed of light to some infinite value actually here in the middle. So we are confronted with the sometimes uncomfortable reality that about 27,000 light years away from where we currently are sleeping and living with our children, there's a supermassive black hole at the very center of the Milky Way galaxy, which around everything is orbiting. Now, the reason why we've discovered it, because there's nothing here actually to see, it draws a lot of information or a lot of matter in, and it doesn't really let a lot of things out, is it does turn out these supermassive black holes do occasionally put out jets of radiation. And so the way we found it was we detected a spurt of radiation that came out of it. The reason why these things exist, these radiation jets exist, it's a little sophisticated and we're not going to get into it, but there's a great article in Wikipedia that deals with this. I encourage you to read it. All right, so what is the architecture of these supermassive objects based upon the escape velocity? Well, let's talk about that. All right, so let's talk about what the event horizon is. Okay, so an event horizon is, in general relativity, a boundary in space-time beyond which events cannot affect an outside observer. So that's a little sophisticated. Let's get out of general relativity and get into layman's terms. So in layman's terms, this is defined as the point of no return, i.e. the point at which the gravitational pull becomes so great as to make escape impossible, right? One of the great things about Einstein is he said, you can never go faster than the speed of light. Light itself can only go the speed of light, and nothing else can go faster. So if the escape velocity is greater than the speed of light, then that means nothing leaves. So one of the questions we can ask ourselves is, what is the radius for the event horizon at Sagittarius A? Notice the speed of light is 300,000 kilometers per second, or what we've already measured is 300 million meters per second. And we actually know what that answer is. We just calculated that on our spreadsheet. And it's embedded actually in this information. It's 12 million kilometers. This is a very large event horizon. Now, does that mean that's how big the star is, or how big the actual black hole, or where the mass is all concentrated? No, it turns out that's not so. So let's talk about the architecture of a black hole. Then we'll be done with our discussion on projectiles. Okay, so we're back. All right, so we have discovered that Sagittarius A, which is at the center of our galaxy, which is the Milky Way galaxy, Sag A is how it's sometimes written as, is a supermassive black hole. So there's a point, let's go ahead and put a circle, and we'll just say there's this mass, M, in the middle. And the escape velocity is greater than that of the speed of light. So that means that at some distance out, there's a radius at which that is no longer the case. Now let's remember what our equation that we're using is. V equals the square root of 2mg over r. So there's some radius distance at which the velocity is less than the speed of light. And this might be, say, at this distance out here. Let's go ahead and draw a nice sphere. Imagine this is actually a three-dimensional sphere coming through here. Cool. It's got some radius. And so at this point, as we transition from across this boundary, the escape velocity, v, is less than the speed of light. And by the way, the speed of light usually gets the letter c as a symbol. So here, v, let's write it as the way we should then, as proper physics students. C is, or v is less than c. The escape velocity is less than c. Let's put it like this. Escape velocity is less than c. All right, but in here, or actually right on this line, the velocity is equal to the speed of light. And then inside, within this radius r, the velocity, or the escape velocity, is actually greater than c. Now, nothing can go faster than the speed of light. So that doesn't mean that things are suddenly accelerating at velocities greater than the speed of light. But what it does mean is that any information that goes into past this dashed line, we can't see. And so the black hole is actually this boundary where the escape velocity equals the speed of light, and then it transitions into a zone where the velocity exceeds the speed of light. This boundary is called the event horizon. Okay, that's the event horizon. And at some point, there's some mass in here. And so it's really hard to know actually how big it is. Current theories suggest that it might just be a little point, something called a singularity. I'll put that word in here. Singularity. Okay. And that's the center point here. And everything here in the middle is this big open black hole. And I'm not even going to color it in because you'll miss it. But you get the idea. This is the black hole right here. And so when we actually measured Sagittarius A, we found actually the event horizon was at 12 million kilometers. But the actual mass itself in the middle could be this little tiny area. But the mass is all concentrated in a very small region. So you get the idea here. So this is the event horizon. It's this big disk, and you can find lots of really fascinating pictures of event horizons, or at least artists' conceptions of event horizons all over the internet. So, all right. And so again, here's the black hole. This is somebody else's idea of what Sagittarius A looks like. Here's the event horizon with the radiation jets coming out and so on and so forth. And some people believe, or at least this artist believed, that this is actually what the center of the Milky Way galaxy looks like, the central object of which we're all orbiting around. Okay, of which if you were to get inside this black sphere, there's no coming back. All right, fascinating stuff. So I hope that you found this as interesting as I do. I really like the astrophysics aspect of it because it makes you think about some of the deeper elements of our existence. And you know, next time you're driving down the road worried about whether or not you're going to pay your bills or not, just remember there's these supermassive black holes sucking things up all over the place. And in the end, we're all going to be cycled into one of these things in, you know, billions of years time from now. So anyways, if you have any questions, of course, send me an email or meet me on the discussion boards. And until next time, have a good one.